This is lesson 8.5, solving exponential equations. We're actually going to do this video in 4 parts because there's a lot of different strategies that we need to take advantage of when solving exponential equations. So we'll do a video for each of the strategies. The first strategy is to take your exponential equation and express all of your powers with the same base. Before we get into actually solving these equations, though, let's review how to change a power's base. So we have 3 examples here, and we want to express each power with a base of 3. So the first one is 1 over 27 to the exponent 2. 27 is a term that we can change into a power of 3 by rewriting it as 3 to the exponent 3, because 3 to the exponent 3 is 27. And if we take advantage of our negative exponent rules, we can rewrite that fraction as, instead of 1 over 3 to the exponent 3, we can rewrite it as just simply 3 to the exponent negative 3. And that whole bracket is squared. Lastly, we can apply the power of a power rule and multiply those exponents. So we can rewrite that as 3 to the exponent negative 6. So there we go. We have a power with a base of 3, and the exponent is negative 6. In example B, we actually have 2 terms. However, in both of these terms, 81 and 27, we can rewrite those as a power of 3. 81 can be written as 3 to the exponent 4. So I'm going to rewrite that as the square root of 3 to the exponent 4. And 27 can be written as 3 to the exponent 3. So I'm going to rewrite that term as 5, the 5th root of 3 to the exponent 3, all cubed. All right, and now we need to apply some exponent rules here. The square root can be rewritten as a fractional exponent of a half. So we would have 3 to the exponent 4 to the exponent 1/2, and if we multiply those exponents, we'd have 4 over 2, which is 2. So we can rewrite that first term as 3 to the exponent 2. The second term here, we have the 5th root of 3 to the exponent 3. We could rewrite that as 3 to the exponent 3 over 5. And that's all cubed. And lastly, we have a power of a power rule here, I guess second to last. So that'd be 3 to the exponent 2, and if we apply our power of a power rule, we'd multiply the numerators. 3 times 3 is 9, so that would leave us with 3 to the exponent 9 over 5. And now lastly, we have our multiplication of powers with the same base. We would add the exponents. Firstly, we'd need to take that exponent and express it as a fraction over 5, so that'd be 10 over 5. And if we add 10 over 5 to 9 over 5, we would get 19 over 5. So a lot of work for that one, but doable. This last example here, the number 15. 15 can't be written, actually let's give ourselves a little bit more room over here. 15 can't be written as a power of 3 directly. However, if we write it in the form we want it to look like, 3 to the exponent something, we can make that something x. And now we're asking ourselves, what value of x in the power 3 to the exponent x would give us 15? Well, we could actually take advantage of our log laws here. Let's use the power law. If we take the log of both sides, we would have log 15 equal to log 3 to the exponent x. And now here's a great opportunity to use the power of a power rule, or sorry, the power law of logs. We can bring that exponent down in front of the logarithm and multiply. So we could rewrite that right side as x times log 3, and our left side as log 15. Why would we do that? Well, if our goal is to figure out what exponent we need to raise 3 to give us 15, because we're trying to rewrite 15 as a power of 3, our goal here would be to isolate for x. And one strategy to isolate for x is to take the log of both sides. And this is actually a strategy we're going to use for solving some exponential equations later on. But I just wanted to illustrate that it doesn't necessarily have to be a power of 3 to be written with a base of 3. Okay, let's finish this off here. We want to isolate for x, so we would divide both sides by log 3. And our right side would be x, and our left side would just be log 15 divided by log 3. And I'll need my calculator here to evaluate that one. Let's see, we've got log 15 divided by log 3. And that's approximately 2.46. We'll call it 2.465. So x is 2.465 approximately. So 15 could be written as 3 to the exponent 2.465. If you want the exact value, you would simply just write log 15 over log 3 as your exponent. And that would be the exact value. Okay, let's apply this changing of bases to solve a couple log equations. Our first one is 25 to the exponent x plus 2, and this on the right side we have 125 to the exponent 2x minus 1. So our goal here is to create a common base. Why would we create a common base? Because once we have a common base, we can set the exponents equal and we can solve. So let's try to rewrite both 25 and 125 as a power with the same base. The power that comes to mind here is 5, a base of 5. So let's rewrite 25 as a base of 5. That would be 5 to the exponent 2. That would all be to the exponent x plus 2. And on our right side, 125 can be written as 5 to the exponent 3. All to the exponent 2x minus 1. And now if we apply our power rule for, a power of a power rule for exponents here, we can multiply the exponents. And we would have 5 to the exponent 2x plus 4. And on our right side, we'd have 5 to the exponent 6x minus 3. Now that we have common bases, we can set the exponents equal to one another. Because if the exponents are equal, when they're evaluated, we end up with the same number on both sides. So let's equate those exponents. 2x plus 4 equals 6x minus 3. And we'll rearrange this and isolate for x. So I'm going to write my x's on the right side by subtracting 2x. So we've got 6x minus 2x. And I'll take my numbers and write them on the left side. So we've got 4 plus 3, which would give us 4x equals 7. So x is just 7 over 4. Oh, can't see that one. Perfect. And of course you could do a left side, right side check here. Plug in your answer to the left side and you should evaluate and get the same value on both sides. Let's try one more. We've got 5 to the exponent 4x minus 3 equal to 1. Now we want to try to write these with the same base, and when we have the number 1, the easiest way to do that is to take the base of the other term. Why? Well, because on the right side we could simply write 1 as 5 to the exponent 0, because anything to the exponent 0 is 1. So when you ever come across a 1 and you want to change the base, pick the base for the other term and write it with an exponent of 1, and you'll be able to solve this quite simply. On our left side, we've got 5 to the exponent 4x minus 3, and just like our last example, we're going to now equate the exponents. So we've got 4x minus 3 equals 0, add 3 to both sides, we get 4x equals 3, and divide both sides by 4, we get x equals 3 over 4. Alright, so there's two examples using our first strategy of changing the base.